So far we've been looking at bosonic systems in this course, and we've been thinking about some kind of system, some quantum spin or some bosonic degree of freedom embedded in an environment which is comprised of bosonic degrees of freedom. However, today I want to talk about another very important class of systems, namely fermion systems. And fermions are the natural system to consider when you have some block of conducting material, which is usually a resistor in this case, and in it you have some kind of impurity or quantum dot. And this quantum dot you can think of as like a cavity for electrons. And it turns out that you can model the conductance, the passage of electrons through this quantum dot using a formalism essentially identical to the one we derived to describe cavities and other open quantum systems. So I want to show you this really important class of systems today. And as a bonus, we get to solve all fermion systems that are quasi-free. So just as a couple of weeks ago, I showed you how to solve all bosonic systems in complete generality, and that formula that we derived for the covariance matrix, you can use that for any quadratic boson system from now on. I'm going to show you today the fermion version of that argument. And this is, of course, of completely independent interest if you ever have to worry about modeling electrons in any setting where interactions are not important. So just as for the bosons, we're going to model this environment here as a bath of oscillators, but this time we're not talking about bosons, we're talking about fermions. So there's some differences that we have to deal with. So we're going to consider models we're going to write down the most general quadratic model of fermions that we can. And this will capture every possible reservoir, every possible environment of fermions that we are likely to encounter. And the way we describe our models is in terms of two matrices, A and B, as we'll see. Oops. So this is the most general model we can write down that involves creation and annihilation operators for n, in this case spinless fermions, although the way to model fermions with spin is just to double the number of modes, one for spin up and one for spin down. The most general quadratic Hamiltonian, we've got terms which have two annihilation operators and terms which have two creation operators. Now usually these kind of terms, these pairing terms, don't appear because of superselection rules. Can't have superpositions of an even and an odd number of fermions. However, these don't actually violate these superselection rules. They can appear as effective terms when you talk about superconductors, for example. We're not going to talk about the right Hamiltonian to use when we're modeling a particular physical example. I'll just hand to you the model whenever we need to study something in particular. So this is the most general quadratic model we can write, and we're going to use a shorthand notation, this vectorized notation here. And in this notation we have a matrix H which has this B and the A matrices inside it like that. So this is a 2n by 2n matrix. And we have this vector of operators here, and I haven't told you what the anti-commutation relations are, but I guess you probably guessed them already. What makes these operators fermion is that they obey these anti-commutation relations here. Now this isn't quite as general as it could be, right? These could be complex matrices. As written, they might be complex, might be real. Let's work out what constraints we have on these matrices here that allow this Hamiltonian to be Hermitian, right? I can't just choose any B and A. They have to fulfill some properties, otherwise this whole thing is not actually a Hamiltonian. So the properties we need, so to ensure that the Hamiltonian is Hermitian, requires that A is real and symmetric, and you can just check that yourself by taking the dagger and comparing the left-hand side and the right-hand side. And that B is real and anti-symmetric. Actually, there is a possibility to make these things complex. That happens when you put a fermion in a magnetic field. However, that doesn't really substantially change anything we're going to say today. We're going to solve this model exactly like we did for the boson case. And we do that by doing some canonical rotations of the operators. But before we do that, we're going to introduce the fermion version of the position and the momentum operators. So these guys here, these aren't Hermitian, right? You know, F is not equal to F dagger. So they're not like the position operator and they're not like the momentum operator, which are Hermitian. But you can build something that looks suspiciously like a position and a momentum operator for fermions. And these operators have a special name. They're called Majorana operators. You may have heard of them recently. You may have heard of Majorana fermions recently, as they've been the subject of a lot of experimental investigations. And it looks very much like they've been observed now. So we're going to introduce some new operators. We can call them C, a vector of these guys. And these operators are very much like the position and momentum operators. They're sums of annihilation and creation operators. Just as the position and momentum operators are sums of creation and annihilation operators for bosons. And we'll just do an example of one of these Majorana operators. We'll work out C1, the first Majorana operator. There's two n of them. The first Majorana operator has the form of F1 plus F1 dagger. And that kind of looks like the position operator. And it has a partner, namely Cn plus 1 in this notation. Which is minus I F1 hat plus I F1 hat dagger. And these are, this is like the momentum. And this one's like the position. And you can calculate that these, further, you can see that these are Hermitian operators. So these Majorana operators are, if you take the dagger of 1, then you get itself again. If you just look at this example here, you can already see that, right? And further, we actually have, oh, wait on, I've forgotten the square roots of 2's. There they are. And we have that these Hermitian fermion operators, these Majorana operators Cj and Ck, they obey anti-commutation relations, very much similar to their bosonic counterparts. So we're going to express everything in terms of these Majorana operators, and then we will hopefully easily see that we can diagonalize our Hamiltonian H. So this is already a huge simplification. Our Hamiltonian now is expressed in terms of a block diagonal, or a block matrix. It's not really block diagonal. It's expressed in terms of a block matrix, but we've zeroed off some entries, and looking at that, we might hope that we can just say diagonalize the V matrix and then get a solution. And indeed, that's exactly what we're going to do. We're going to take this matrix V and we're going to process it to get a simpler matrix. And we're going to find that that corresponds to a unitary transformation on our Hilbert space. Now, the first thing to note is that V, as written, isn't Hermitian. A is symmetric, so this part's symmetric, but if we transpose the second guy, we get a minus sign. So it's sort of nothing, really. You transpose it and you get a different operator. That means we can't expect to diagonalize it in terms of orthogonal matrices, but we can expect to be able to use the singular value decomposition. This is the go-to linear algebra process when you have a matrix which is nothing, right? Nothing special, neither Hermitian or anti-Hermitian or anything like that. Every matrix has a singular value decomposition. And this V matrix here is no exception. And because it's real, we can use a singular value decomposition to write this matrix as a product of three matrices, two of which are orthogonal. And one of which is diagonal. Oops. you can always do this. For any real matrix. And the way to remember how to get this decomposition is you can get O1 by diagonalizing V transpose. V transpose is a symmetric matrix, so you can always diagonalize it using an orthogonal matrix. And you can get O2 by diagonalizing V transpose V. So now that we've got these O1 and these O2, these symmetric matrices, we're going to introduce new fermion operators. We're going to make a canonical transformation. Now there is some potential for confusion here with the notation. O1 is an orthogonal matrix, but this is the matrix of all zeros. I suppose I could do this. But then I'd be worried it looks too much like theta. Well, I suppose that's okay if we define theta to be the matrix of all zeros. So, all right, this canonical transformation here, you can check that it preserves the fermion anti-commutation relations. It's an exercise. So there's 2n, 2 times n.
Yes, but O2 has already...
O1 has n, is an n by n matrix. So A is an n by n matrix. Oh, I've erased it already. Oh! Oh, yeah. Oh, that was wrong. Yeah. Okay, these are n by n. The sigma's 2. Yeah, that's absolutely right. Goodness, thank you. That was. So these are n by n matrices. because A is an n by n matrix and so is B. Well, I've erased them. And now I hope everything is correct. So V is an n by n matrix. Yeah, so we've got these new operators C prime. Let's see what happens to our Hamiltonian when we express it in terms of these C prime operators. So I've just gone ahead and substituted for C prime, C in terms of C prime here. So changing to these new Majorana operators C prime, when we express our Hamiltonian, when expressing our Hamiltonian in terms of the C primes, we don't get something that's diagonal. If you look at this, it's clearly not diagonal. It's even got zeros on the diagonal and something on the off diagonals, but it's as good as diagonal because these D's are diagonal matrices here. To make it actually diagonal, we're going to make one final transformation back to some fermion annihilation and creation operators. And then we'll see that this model has been diagonalized by this transformation. So this is our final redefinition. If we define these operators B, these are now no longer Hermitian operators, they're creation and annihilation type operators. Then we will obtain this Hamiltonian in a form that's a bit more familiar. So this doesn't look diagonal, but I assure you that it is. So when you express everything in terms of the B's, then you see that we've got a bunch of n decoupled fermion oscillators. And we can work out the ground state of this model very, very simply. So fermion oscillators are much simpler than boson oscillators. So a fermion oscillator only has two dimensions, a two-dimensional Hilbert space. So if you have some Hamilton operator which looks like this, and these are fermion operators, then that is equivalent to a 2 by 2 matrix with a 1 in the second entry. And we have two states in our Hilbert space, the space where there's no fermion in the system and the space where there's one fermion in the system. So fermion oscillators are super duper easy to solve. The ground state's always just the empty state. And the only other state in the spectrum, or in the Hilbert space altogether, is the occupied state. You can't have more than one fermion in the same mode, so that's all we can expect in our Hilbert space. So in very many ways, fermions are easier than bosons, and here's yet another manifestation of this. Fermion oscillators they're no big task to solve. And many body fermion systems, like this one here, have a Hilbert space which grows with the number of particles. It's a finite dimensional Hilbert space. It's the other good thing about fermions. So the Hilbert space we have to worry about for n fermions is 2 to the n dimensional rather than infinite dimensional, which it would be for bosons. So if you look at the Hamiltonian expressed in terms of these B operators, you can see that it's just n independent fermions, oscillators. That means we already know the ground state of this model. In fact, the ground state is unique unless one or more of these sigmas are 0. Remember, all of the sigmas are bigger than 0. So this may seem at odds with what you know about Fermi seas, but I'll explain that in a second. So the ground state space of H is either one-dimensional, in which case there's a unique ground state, or it's degenerate if there's more than one of these sigmas, which is 0. So the ground state space, I should say space, so it can be that the system has more than one viable ground state. And the number of ground states you have is n, the number of fermion modes, minus the rank of V, all to the in the exponent of 2. Now we're not really going to worry about the case where the rank of V is not n. We're going to assume that V has full rank. You can sort of convince yourself that that's a reasonable thing to do, because the minute you have any kind of disorder or randomness in your system, it's likely to lift any kind of symmetry and degeneracy. But one must be a little bit careful about ranks of operators with fermions, because we often encounter systems with symmetries, and there it's possible for this operator to have a non-full rank. Let's not particularly worry about that in this course. Everything I can say can be adapted quite easily to the degenerate case anyway. Well, we know the ground state, yeah? So the ground state is just the empty vacuum in terms of these B's. Now this seems at odds. I hope that you were already sort of concerned that this looks different to what you might know about fermions, especially metals. So you've probably learned that a metal has a description in terms of a Fermi sea, and that's definitely not empty, right? That's full of fermions. Now, there's no contradiction with what we've derived here. The thing is, these B's are not the original fermion operators. They're some superpositions of fermion operators. And when we express things back in terms of our F's, we'll see that this ground state has actually got very many particles in it in terms of our original operators. So these are fantasy operators. These aren't real. These help us diagonalize the system. Before I show that, I just want to show you, well, we've worked out the entire spectrum, all the eigenvalues. Yeah, I'll write that in a second. Let's worry about let's worry about the gap between the ground state and the first excited state. First, So I'll explain where this number comes from. We can work out all the eigenvalues of our model. They're just sums of these sigmas, as we'll see. Let's just start listing the eigenvalues of H. Well, the lowest one is the eigenvalue attached to the ground state. And that's when you've put every mode into the empty vacuum state. You have no B-type fermions left. If you apply this operator to the ground state as defined over there, then we can work out immediately the ground state eigenvalue. It's j equals 1 to n minus a half sigma j. I've just applied the model H to the ground state. Oops. Now we can construct excited states. How do we do that? We just put a fermion in one of the n modes. And the energy associated with putting a fermion in the jth mode, we can work that out. Just look at that expression up there. It's the same thing as E naught. And then you've got to add on sigma j, I think. Let's check that. Yeah, I think that's correct. And then you've got two particle states. And we set j less than k. And so on, right? And the energy of the n particle state, where every single fermion mode is occupied, is this here. Wait on. That expression there. So let's look at these numbers now. You've got a negative ground state energy E0, Then we've got these first excited states, Ej, 2 particle states, 3 particle states, 4 particle states. And every one of these eigenvalues is bigger than the previous one. And the reason is we're always adding on a positive numbers. Sigma j, sigma k, they're all non-negative numbers. So we can work out the gap now between the ground state and the first excited state, because we've just determined that the first excited state has to be of this form. So the gap is obviously the ground state energy, the first excited state energy minus the ground state energy, but which first excited state? What's the right one to choose to get the gap? And the answer is, well, you just find the minimum of these sigma j's. And in my notation, that means the smallest eigenvalue of VV transpose. So we've just diagonalized pretty much every quadratic fermion model you're ever likely to encounter, which allows you to talk about metals, which allows you to talk about the Dirac equation, which allows you to talk about Majorana fermions in near superconducting wires. So it's sort of worth stressing that this result is completely general. There's nothing here that's specific to any particular model, except that it's quadratic. So in this course, we've unlocked 2 of the most general models possible for the description of quantum matter. And for the rest of the course, we're just going to exploit this general result like this. So this is really worth remembering and spending some time understanding this result, because it will save you plenty of time in other courses. In other courses, you spend 20% of your time diagonalizing this or that quadratic model. But you've done it in general now, so you just need to remember these 2 approaches, and you have everything you need. All right, so the ground state for this model is Gaussian. I'm going to put it in quote marks because it's not quite clear what that could mean in the fermion setting. In the boson setting, it's clear. You work out its characteristic function and you find that that's a Gaussian function. But we don't have a notion of a characteristic function here. Well, we do in terms of things called Grassmann numbers, anti-commuting numbers. I think the energy we need to expend to learn that formalism in this course isn't worth the payoff. So we're not going to do that, and I'm just going to give you an ad hoc definition for what Gaussian means in the fermion setting. And what it means is that it's determined by its second moments, just like any other good Gaussian is. And to express that, we're going to define the covariance matrix for a fermion model. Just as we would for a boson model. Okay, there's definitely a large potential for confusion in the notation I'm about to use. Try and explain this. Now this covariance matrix gamma is a 2n by 2n matrix. So notationally, this is potentially very confusing here. We've got this vector of B operators, which is a 2n dimensional vector, and I'm taking the jth index. So this B's and B daggers in B hat bar, and depending on J, this is either a B or a B dagger. So there's 4 types of terms you can have in the covariance matrix gamma prime. You can have BB type terms, you can have B dagger type terms, you can have B dagger B type terms, and B dagger type terms. So that's why it's 2n by 2n matrix. So, and the notation is this. So I've used 2 types of notation which have an easy chance of being confused with each other. One is just Bj, which just means the annihilation operator for mode J. And the other is take this 2n dimensional vector and find its jth element. That's a different thing unless j equals 1 to n, in which case they're the same thing. Now for us, this gamma matrix is incredibly simple. It's just this. The only way you can get a non-zero answer is if you've applied a B dagger and then a B, because otherwise you annihilate the ground state.
Particular reason why you named this matrix gamma prime and not gamma?
Because it's in terms of these B's,
Okay.
and we're going to find, eventually we're going to undo all our transformations to get back to a matrix in terms of F's, and F's are the real fermion operators, and they're the ones we really need to care about. And that's what we're going to do right now. Well, actually yeah. Oops. We actually define covariance matrices in terms of C's rather than F's. This is so that the whole formalism is analogous to the boson version, where the covariance matrices are defined in terms of X's and P's. So the usual way to express covariance matrices is in terms of the X and P's in the boson setting, and in the fermion setting we should do it in terms of the C's. And it contains all the information we want from our system. So for us, we get the following expression for the covariance matrix when you work it all out. and undoing the transformation to C, we can actually work out what the second moments are for the F operators. Basically done. So in one fell swoop, we've worked out all the second moments of our model now in terms of the original annihilation and creation operators. Is V bar the complex conjugate of V? No. So yeah, that's another potentially confusing notation. V bar is just another matrix defined by these O1s and O2s. It's like diagonalize V and then take the D out the middle. It's called the spectral flattening. But yeah, I don't imagine you've encountered that terminology. You could easily spend your life studying Gaussian models, either Gaussian bosons or Gaussian fermions. The thing about Gaussians is you can say everything about their eigenvalues and eigenvectors, so you can ask very complicated questions of a Gaussian or a quasi-free model and get answers to your questions. The more complicated your question, the harder the answer, but you can at least go quite a long way. Going away from these Gaussian class of models, these quadratic ones, there's not much you can say in general. But we often use these quadratic models as a starting point to describe physical systems. We completely solve these and then we add in a small perturbation. And then we use perturbation theory to understand the system. This is really, most of physics is described on these boards. I just want to say, or recall the point that the ground state of this model is not empty. There are fermions in this ground state. So the ground state is not necessarily empty. Let's calculate the average number of fermions in our original variables in this ground state. So there can be as many as n fermions in this ground state, depending on what this V bar does. So the number of fermions in the ground state is n over 2, half the system, half filled, minus whatever this number is here. And this number can vary between minus n over 2 and n over 2, depending on what O1 and O2 are. So you can go from a situation where there's no fermions in the ground state to the ground state is every single fermion mode is occupied. And the kind of situation where you'd expect to see that is when you have free fermions hopping in the presence of a chemical potential, which enforces that the filling of the system is at some number. This is the kind of situation you have when you have a conductor. Conductor is a free fermion model, and you keep it at some chemical potential, and that's why there's fermions filling up the ground state up to some cutoff point. Now in the last part of this lecture, we're going to use this result to derive a master equation describing the tunneling of fermions through a quantum dot between two fermion reservoirs. So this is the closest analogy we have in fermions to a cavity, an optical cavity. An optical cavity is actually coupled to two different boson reservoirs. There's the in modes and the out modes, right? Oops. So you can really think of a cavity as connecting two reservoirs. But for bosons, the in modes are usually in the vacuum and the out modes are usually in the vacuum, or they're both in the same thermal state. For fermions, we have a different kind of situation where you can have the collector and the drain being at different chemical potentials. You can also have this for bosons, but this is a bit more harder to construct. So if you think about bosons, we have this situation where we have a cavity, and this cavity is coupled to two reservoirs, right? The modes of light coming in and the modes of light coming out. So what I'm about to describe now is a fermion version of this picture. So here's the picture you're going to see in any talk on quantum dots. We have some colors. So we imagine a quantum dot embedded in a resistor, and this quantum dot has been arranged so that it's very, very cold. We're talking about 1 Kelvin here, so that the quantum dot can support at most one fermion. So it's like an artificial atom with one mode, or one orbital. and it's connected by tunnel junctions to two different fermion reservoirs. I'm just going to describe the physics in words. We're actually just going to write down a model in the end, and I'm not really going to justify it. I didn't draw this tunnel barrier high enough. Yeah. So these tunnel barriers are set up so that classically no fermion can get from the C into the dot, and no fermion in the dot can get to the other fermion, C. We call this the left and the right reservoirs. They're held at chemical potential mu source, mu drain. There's some charging energy for the dot. We have some tunneling rates gamma L and gamma right. And the height of this barrier is adjustable. And the difference in chemical potentials between the source and the drain is E times by some potential bias. You don't really have to understand the physics of this beyond a metaphorical level, because I'm just going to write down a Hamiltonian that models this and refer you to a solid state physics course to derive that. All right, step one is to assume that this dot here, this quantum dot, has a single bound state. With energy EC. It's a fermion system, so it's a fermion oscillator, so it's two-dimensional. Okay, we're going to assume that this dot is connected by tunnel junctions to two fermion reservoirs. These are analogous to the incoming modes and the outgoing modes in an optical cavity. We're applying a bias voltage across the source and drain. And what about these reservoirs? Well, these reservoirs are just a free collection of fermions moving around in one dimension or two dimensions or whatever. And they're held at a chemical potential mu, and they're at thermal equilibrium. The only difference between these two reservoirs is that one is at a higher chemical potential than the other. And after all these pictures and words, I'm just going to write down a Hamiltonian, and that's what we're actually going to study. So you have to believe me that all these words can be justified to give a Hamiltonian. That's not easy. That's some hard physics that we're not going to do. Once we've done the hard physics, we're going to come up with this particular Hamiltonian here. So the Hamiltonian is the Hamiltonian of the quantum dot plus the two leads which go into the quantum dot. And it's very simple to write out. Knowing that we can diagonalize fermion models, we've exploited that information here to write that each fermion, that we've already diagonalized the fermion model for the reservoirs, the source and the drain. Well, here's our model. And there is some potential for confusion here, again, because we've got so many fermion operators that I've overloaded notation here and called by C the fermion operator for the quantum dot. And the confusion comes with the C's. The C's are no longer Majorana. They are not Majorana operators here. And these T's, these are the tunneling rates, or matrix, tunneling coefficients actually. These are small numbers because these are classically forbidden transitions to go from the source to the dot and from the dot to the drain. So there's a very small matrix element between those wave functions. And the last bit is, well, these are free fermions moving in the reservoir. So we can actually work out these energies. It's just the non-relativistic kinetic energy. So these are free fermions moving in reservoir 1, the source, and reservoir 2, the drain. And the energy per fermion is just the, in the momentum basis, the standard non-relativistic kinetic energy. So there's a couple of things we could say about this model straight away. And, after we've done the hard physics and arrived at this Hamiltonian, once we're there, actually we can say a lot about this Hamiltonian. We can say just about everything about this Hamiltonian because it's actually quadratic. If you look at the model itself, every single term appears at most with 2 fermion operators in it. So we could just straight away diagonalize this and study the dynamics of this. However, we're not going to do that, just as we didn't for cavity emission. In the cavity emission case, we also had a Hamiltonian which was quadratic, which we could have just solved analytically. I mean, you can do this, but this doesn't give you any insight into how you get the equation of motion for the cavity alone, or in this case, the dot alone. So we're going to apply, in the next lecture, we're going to apply the same derivation that we outlined a couple of lectures ago to derive this Born-Markov master equation. So I think we might I'll just mention the setup we're going to study in the next lecture. We have this total Hamiltonian H0 plus V. And at time t equals 0, we're going to have the tunnel junctions up very high. And so the initial state, rho initial, will be the ground state for the source tends to the ground state for the cavity, for the dot. Tends to the ground state of the drain. And this is the ground state in the presence of a chemical potential, so it's not empty. So these two reservoir states will be filled with fermions up to some Fermi sea level. And then we let time go on and trace out the reservoirs. And this is for next lecture. But I want to say some comments about when we expect this to be even good. When does this actually work? And the answer is when there's a huge resistance between the source and the drain. This kind of, this is fairly general here. The derivation I'm going to show you in the next lecture, which will be this Born-Markov type master equation just for the dot alone, that will only work when there's a small rate of fermions hopping into the dot, and then there's a small rate of fermions hopping out of the dot. If you go outside of that regime, then these approximations that we used in the previous lectures, and I'll use in the next lecture, they won't work. And you have to go to another description of the model. And so this typically doesn't work, and in fact, at room temperature, if you have a dot, the way you study the physics of such systems is completely different. It's only at extremely ultra-cold temperatures do you expect these approximations that I'm going to show you in the next lecture to work, where the fermions sort of one by one tunnel from the source to the drain through the dot. But now seems like a reasonable point to stop before we move on to that derivation. So I thank you very much for your attention.